Our next speaker is Igor Ivaniuk, Senior Solution Architect at AWS. As a solution architect at AWS, Igor helps customers to implement their know-how and grow business with help of cloud technologies. His primary interest in DevOps, containerization, serverless, and blockchain area. Before joining the Amazon, Igor used AWS as a customer, building solution and helping companies adopt cloud technologies in fintech, e-commerce, banking, blockchain domains. For the past 30 years, he has worked on Java project, done some Golang, Scala, and Kotlin development. Then, as a solution architect, took responsibility for transition the legacy e-commerce monolith to the microservice in AWS cloud. And for the last few years, he has focused on cloud transformation in fintech companies and blockchain projects. Today, Igor is going to share his experience in efficient scaling of Kubernetes cluster. Personally, I'm waiting this session for the whole day. Hi, Igor. How are you?
Hi, Dmitro. Just one quick question. Should I continue in English or we can just switch to Ukrainian maybe?
We have guys from Bulgaria, Poland, Romania,
Right.
so we should
Right.
continue
Okay.
in English. Yeah.
Okay, then. Just one little bit correction. I don't have 30 years of experience. I have 13. So I'm not that
13.
senior.
Sorry. Yeah,
So,
but 30 is
right.
still okay. You will
Yeah,
have.
hopefully.
So, stage is yours. Please go ahead and share your presentation.
Sure. Okay. Hi, everyone. Big kudos to the survivors who managed to stay till the end of the session. Uh, Believe me or not, the last session by Darko will actually give you energy for the rest of the week. Just bear with me for a second. So it's Thursday evening. It's pretty dark outside. There's storm actually outside of my window. So sorry for some background noises. And I think it's a perfect time to talk about Kubernetes cluster scaling. So we all know that how Kubernetes cluster and how the pods, how the workloads in the Kubernetes tend to scale. And normally when we start talking about that, we talk about pod autoscalers. There are horizontal pod autoscaler, and the idea of it is that you have pods, so you have your applications. You define some metrics for them. They can be usual metrics like CPU usage or memory usage, or maybe requests per second, for example. Or you can even use some custom business metrics. And based on that metrics, you publish these metrics somewhere into a metrics server. And then you have an external entity, the pod autoscaler, which will make sure that the average utilization of these metrics, so average value, for example, CPU utilization, is as close to the target as possible. And it will either add new pods when you are running out of resources, or remove them if the load was reduced. So it works automatically, and it works in an infinite cycle just by checking the metric server. So your Kubernetes pod shares the metrics, puts them into the metric server, and pod autoscaler uses this data to scale. It's horizontal, so it just increases or decreases the number of pods. Of course, you also have vertical pod autoscaler. Well, its benefits are that you don't have to define individual pod resource limits if beforehand, because what it can do on demand, also reacting on the change in load, it can change basically the size of the pod. So the number of resources which are dedicated for a specific pod. It also supports scale up and scale down, and usually it is used for the pods where you expect to be some either single instance of an application, or some finite number of instances, fixed number of instances. So you cannot uh, scale them horizontally, but you have to keep the exact number. But to react on change in load, you can also scale them vertically. Nevertheless, all those scaling are touching pods. But what happens if you don't have enough resources in the cluster? Usually you talk about closed cluster autoscaler. So how it actually works? Uh, let's assume that your load is higher and you have horizontal pod autoscaler trying to launch more pods. But as you see on the diagram below, there are not enough free resources in your cluster. So you have only 4 nodes, which have only, let's say, one unused vCPU. So cluster autoscaler tries to accumulate those pods. So it sees that there are pending pods and launches new nodes to fulfill this requirement. So I think it's like it's all good. I think you all know about that already. But is there something that we can do better? The thing is, with cluster autoscaler, it works, but there are some flaws to its design. First of all, usually when we are talking about autoscaling groups that are managed by cluster autoscaler, it is recommended to have the same size of the instance in one autoscaling group. It's natural because cluster autoscaler will rely on that similar size and will calculate the number of new nodes based on the number of previous nodes and the resource requirements in pending nodes. So if you are and it means that, for example, if your nodes are pretty big, so the scaling steps, the size of the new instances that it launches are also big and they're fixed. You cannot modify them. And it means that, for example, if you have pending pods, like very small pod, but it just barely overflows the capacity of the cluster, the autoscaler will just launch a new instance, and most resources of that new instance will be unused. And also, I would say that the speed of scaling with cluster autoscaler could be better, because cluster autoscaler doesn't launch the instances directly. What it does, it just changes the desired count of the autoscaling group, and then so first you have some delay for horizontal pod autoscaler to increase the number of pods based on the load. Then it takes some time for cluster autoscaler to discover that there are pending pods that are not possible to schedule in the cluster. Then cluster autoscaler modifies the desired count. Then it also takes some time for the autoscaling group to see that the desired count is different. And finally, the autoscaling group launches the instance, which also takes some time to ramp up. It means that it can take, I don't know, between few up to, like, I don't know, 5, 7, 10 minutes until finally your new load, your new customer load can be served by new pods that are scheduled on the new nodes. Let's try to solve this. Some time ago, actually on previous reInvent, we introduced Carpenter Cluster Autoscaler. It's an open source project, so it was developed in AWS, but it's now fully open source, hosted on GitHub. And its main target was to fulfill these requirements to make the scaling more elastic and faster. So how it actually works? Usually with cluster autoscaler, you have horizontal pod autoscaler scaling number, increasing number of pods. Then there are pending pods. Then you have cluster autoscaler triggered. Then it triggers autoscaling group, and then autoscaling group finally talks to the EC2 API to ramp up new instances. With Carpenter, you just throw away those intermediate steps. So Carpenter analyzes pending pods and launches EC2 instances directly without autoscaling group. That's why it's also sometimes called groupless autoscaler. And how it actually schedules. It works in tandem with Kubernetes scheduler to find the pending pods and with compute provider. So first of all, if you try to launch new pods or if horizontal pod autoscaler launches new pods, kubescheduler first checks what kind of capacity you still have in the existing nodes. If there are some, the nodes will be scheduled on the existing resources, of course. And then Carpenter observes the unschedulable pods. So the number of pods that are, for some reason, unschedulable, either because of absence of resources, or maybe because of some scheduling constraints. But we'll talk about that a little bit later. And then finally, Carpenter just checks and schedules how many. So it checks how many resources are there, how many pending resources are needed, and it chooses just the exact instance or instances which will fulfill that capacity. It's not limited by specific instance sizes or types. If you don't limit it, it always tries to find the instance which fulfills the requirements the best possible way, so to have the least amount of unutilized resources. So if you get back to the previous diagram, what would happen? First, of course, you have some pods scheduled on unutilized resources, but then Carpenter will just launch one new node bigger than others to schedule those nodes, those pods that were pending. It uses the bin packing algorithm, which is very similar to well-known like backpack problem. So how to optimize the capacity depending on the resource requirements. So there are different ways how to configure or limit these changes or these the instances types or the resources that Carpenter can provide, and we'll talk about its configuration a little bit later in details. Carpenter also is able to scale in. So if the resources are not longer needed, if the node is free, it first applies the TTL. So you have a configurable parameter to tell how much time to wait until node scaling, and then, well, destroys the instance. How to configure it? Yeah, by the way, one important feature to know that right now Carpenter doesn't support pod eviction, so it cannot do like defragmentation right now. So it can, if you have a lot of pods distributed on multiple nodes, and it's not really efficient. Right now, Carpenter cannot do it, but there is a feature request. I think it's one of the most upvoted feature in GitHub for Carpenter to allow the fragmentation. So to allow you to pack the pods tighter into the remaining nodes. So if there are some unutilized capacity, you can, according to some policy, like kill some pods one by one and just restart them on more utilized instance to free up unused resources. How does it work? With Carpenter, it introduced the concept of provisioner. Provisioner is the configuration which will define how exactly you would like Carpenter to launch other instances and what would be the restrictions. You have to have at least one provisioner, it's the default one, but you can have more if you need to isolate, if for example you need to isolate some resources according to different needs, or if you need to follow some specific requirements, like for example GPU presence, or if you need to follow some taints, or even follow the node affinity or node selector specifications. During the setup of Carpenter, you would have to create the default provisioner. It will pick up the one that's more specific. You can work fine with one provisioner. So you can use single provisioner for all the cluster, of course. And at the same time, there is no if during the scheduling of the pods, it turns out that multiple provisioners can be used for that pod. So because of limitations or conditions, Carpenter will just take the random provisioner. So it's better not to have like not to have catch-all provisioners, because otherwise you will have unpredictable behavior, let's say. This provisioner configuration has multiple entries. You have labels, requirements, taints, limits, and provider. So let's go on them top to bottom. So labels are, well, labels. So labels means that these labels will be applied to the resources, to the instances scheduled by Carpenter. So you can use, I don't know, use your application name tag or whatever you like. And then we have parameters. TTL, two TTLs, seconds after empty and seconds until expired. Seconds after empty means that, that's the TTL which will be followed before decommissioning the node. Which means that as soon as the node is empty, in 30 seconds it will be switched off. And then if you have pod expiration, you can define the TTL until the pods are expired. Regarding requirements, you can define a lot of requirements. We will talk about them a little bit later. But the main idea that here you basically define what kind of resources you would use, whether you would use spot or on-demand resources, what kind of availability zones you would like Carpenter to use. By the way, that's another benefit of Carpenter versus cluster autoscaler, because if you have applications working in multiple availability zones, using cluster autoscaler, it doesn't guarantee you which availability zone you will use. So either you create multiple autoscaling groups per availability zone, and then you have to configure a cluster autoscaler to use specific autoscaling group, and then be sure that it goes there. Or if you have one autoscaling group, which you can have in AWS now, stretching over multiple AZs, then basically the new instance will be chosen randomly based on some capacity and so on. So it may require a few attempts to get the instance in the correct availability zone. Also, in the provisioner, you can define taints, and if the pods do not have a specific taint tolerance, they won't be able to be scheduled with that provisioner. So you can use taint somehow to regulate which pods should be scheduled by which provisioner. Then you have limits. This limit is basically defines the maximum resource limit for your whole cluster. It is limited in, for example, in CPU cores, because Carpenter can schedule instances of different size and of course produce different scaling steps. That's why, but you can limit the total number of cores for your cluster. So if something goes wrong and if your application just scales out of control, you can still be sure that it won't use like too many resources. And the very last item, the provider section, is the section which is related to compute provider. And these are the configuration which is specific to the cloud that you would like to use with Carpenter. At the moment, there is one compute provider, which is AWS, and in this provider, you can you put some configuration which is related to discovery of cloud resources. For example, here you need to define security group selector. So to define which security groups should have the pods in there, you use a parameter. Basically, this parameter tells Carpenter just take the one, just take the parameter, the settings, the security group settings from the Kubernetes cluster, and you would, or alternatively, you can hard code some security groups if you like. Let's go a little bit more into details into the requirements. So in the requirements, you have different purchase options. Of course, you can use either spot or on demand, or you can also limit the architecture that you would like to use. Then you can use, for example, ARM 64 if you are using the Graviton CPUs, and you and your applications, your pods are compiled to be used with gravitons, you need to choose the architecture, RM64. By default, it uses only x86 architecture. Um, Usually, you don't have to put a specific list of instances because Carpenter will try to select the best instance for your workload. It will rely, so its algorithm relies both on instance memory, instance CPU, and of course, and also instance price. So, but if you would like to do some limitations, to choose, for example, just two instances, large and extra large, then you can do it in the requirements as well. And define availability zone. And this is the way how you can restrict availability zones if it makes sense for your specific use case. When the nodes are being scheduled, you can use different features of node selector and node affinity together with Carpenter as well. For example, in your pod definition, you can very well use the capacity type from Carpenter to make sure that this pod should be scheduled on the spot on the spot compute. Also, in node affinity section, you can use the same approaches to use topology parameters, and you can also take parameters from Carpenter itself. Like for example, this combination of node affinity will make sure that the nodes can be launched only in zone US West 2A, because first of all you allow two zones, and then you exclude one of them. When you use node affinity, you will have actually two types of the usage. It's like hard or soft limitation. If you have required during scheduling, then it is required. So if it's not met, the pod won't be scheduled. If it's preferred, then yeah, it's preferred. But if it is not fulfilled, pod still will be scheduled on a different node. And now let's see a little bit how this all works. For that scenario, I tried to do some load testing on the cluster. And actually, I had two clusters. One was scaling with Carpenter, another was scaling with classic cluster autoscaler. And so these were my configurations. So in cluster autoscaler, I limited the instances types. But because actually this configuration is not even the part of the cluster autoscaler, it's the parameter of the node group. And as you can see, you can have only large instance type here. Because in my case, my managed node group supports only one size, as actually recommended by the documentation. On Carpenter, I just defined that it has spot instance type, the limit, and the TTL that we were talking about before. I also launched kubeops view to visualize these results. So how do you think what happened? If you launch 100 pods, 100 vCPUs, 100 gigabyte of RAM requirement. Cluster autoscaler, as you see, launched many large instances, just a lot of them. Carpenter instead launched just one instance. So this on the left, this was the original node which was running kubeops. So Carpenter just added just one new instance, which was enough to schedule all those nodes. Let's increase the granularity and the number of pods. This time the pods are smaller, just 250 milli CPUs and less RAM. Carpenter this time decided to split the workloads to two, and it actually chosen two different instance types. You see, one 16x large and one 12x large, to efficiently utilize all the resources. Cluster autoscaler, the same behavior, just launch a lot of large instances. Then let's try to launch something bigger. For example, let's launch a pod which requires 10 CPU and 10 gig RAM. Cluster autoscaler was not able to schedule them, of course, because our instance size, the large instance size, so means that one node is not enough to run this pod. Carpenter, as usual, just launched instance, two instances of M6A 32x large. Scaling down works as well. So when I was scaling down, I was able to notice that of course, if the node is free, it gets scaled down. You can control the granularity of the distribution of the pods. So how big instances the carpenter should use. So you can either define the set of instance sizes that you would like it to use, or you can use topology constraints. For example, this time I launched the configuration with topology constraint of max Q30, which means basically the max, let's say, the max scheduling parameter, so to say, should be 30 or more. So scheduling distribution parameter. But with this scenario, this distribution parameter is actually equal to number of pods per node, so to say. And you can see as a result, instead of launching two big nodes, as we see before, Carpenter obeyed these constraints and launched 15 different nodes, each of them having not more than 30 pods per node. And that concludes my discussion, my session. And now I would like to see if there are some questions, and I would like to hear what do you guys think about all that.
That's awesome. I'm just realized. Are you author of Carpenter or not? You just
I wish I
integrate.
was. I wish I was, but no, not yet. But it's open source, so everyone can be. And I know that
Mhm,
there are a lot of community requests. So Carpenter is actively developed. So when it was announced, the version was 0.5. I believe now it's something like 0.11 or 0.15, and so there are a lot of changes. For example, during initial launch six months ago during the event, there was no way to satisfy node affinity and node selectors. But now with the version 0.9, they have added it.
mhm,
So it's it's actively developed at the moment.
mhm. So potentially, this tool can help with achieving sustainability, right? To save some electricity, maybe price, right, for the clusters potentially. Do you know some
Yeah,
insights using?
yeah, that was the initial idea because the whole idea behind Carpenter is to utilize the resources as effective as possible. And we are all waiting for the fragmentation option to be implemented. So I've done my research as well a little bit to see. I think it's actually it won't be too complicated to implement. So there are some branches that where actually we are already working on this. So as soon as it is done, you will be able to also not just to schedule the pods, but also like move them, relocate them between nodes, and it will. I think it will be the way to achieve maximum elasticity, because
Mm-hmm.
you can consider two different dimensions of that. One thing is you can even you can move the nodes. That's one option. You can move the nodes to one instance which is unutilized. But what if this instance is still too big? So this could be a next step. You can launch a smaller instance next to it, then migrate all pods to this smaller instance, and then just shut down the bigger one to
Yeah.
achieve the maximum the maximum efficiency if
Mm-hmm.
your system allows this kind of pod termination.
Awesome. That's great. I'm just thinking about, we for the last decade we are talking about horizontal scaling, right, and elasticity, but vertical scaling was bad practice for a lot of applications. So, and it looks like the compromise trade-off between horizontal and vertical scaling, right, something like that,
Mhm.
the combination of both.
Well,
That's
you
interesting
are
approach.
you are very welcome. So Carpenter is responsible only for cluster scaling, so you are very welcome to use either horizontal or vertical autoscaling. Carpenter doesn't care much. It looks only on the total amount of resources that are unscheduled yet.
Cool. And following this answer, we have a question from audience. For scale up and scale down, does AWS recommend to use Carpenter over cluster autoscaler?
Um,
Be careful.
so, hmm, yeah, actually, I think the answer is most probably because right now, um, Carpenter. I think I forgot to mention it, but Carpenter also supports providing the launch templates or the EMIs to be used with the with the instances. So the only limitation I see here is that Carpenter does not utilize autoscaling groups. So if you have
Hmm.
some systems which rely on autoscaling group for some reason, for example, if you are using it with load balancers, which use like auto provisioning of the instances in target group for the load balancer, then
Hmm.
this could be a limitation here.
That's right. Yeah, makes
That's
sense.
why
Makes sense.
cluster autoscaler still exists.
Hmm. Uh, am I understand correctly? So if we using Carpenter and we need the biggest node, right, for manage all our pods. So how we can guarantee that this node actually exists in availability zone or region for our needs right now?
Um, this question is a little bit not related to the Carpenter as such, because of
Hmm.
course, when you use it with the AWS compute provider, it just interacts with the EC2 API, just querying it if you have these resources or not.
Okay.
And of course, Carpenter in this situation is working with the changeable load, so it will be used either with like on-demand instances or even more with spot instances. Um, if you would like to schedule very big nodes and you know that they are so you have to have them ready. So if or if you are using some, let's say, exotic or not so common instance types, like for example big instances that also have GPU adapters,
Hmm.
um, I think well the only guaranteed way to have the capacity is to use capacity reservation, because capacity reservation is basically the way how you can book compute for you. But as soon as you create capacity reservation, you start paying for it.
Hmm.
So it doesn't. And then if you're already paying for it anyway, it doesn't make sense not to launch instances and just pay for the reservation.
Yeah,
So with
that's
this scenario, we are drifting towards, let's say, fixed model. When you have the fixed number of instances, you pay for them all the time.
right. Yeah, and am I understand correctly that, for example, if the customer have a lot of reserved instances, in this case, they probably better to use native Kubernetes with cluster autoscaler and avoid the Carpenter, right? Because we
Well,
already paid for some instances, and in this case, we lose some
yes,
benefits.
yes, but what I see now is that more and more customers are preferring to use compute savings plans instead of reservations, which are much more flexible, and they can be applied to any type of instances and actually any type of computer resources. That's why if you can do, I mean, if you still have reservations, like okay, keep them only for because I mean still reservations are the way to get to get the biggest discount. So the cheapest
That's right.
way to learn something is to have reservations. But so I advise my customers to create reservations only for the non-flexible workloads, to something that
Mhm.
they will use constantly, and they are sure about it. And
Yeah,
for
like
so for the workloads, so you can limit to those types of workloads. And for the clusters which breathe, which tend to scale up and down, it's better to use saving plans instead of reservations.
awesome. Thank you for advice. A really nice tool. I need to look at it deeply. So thank you for your time. Great presentation. And yeah, thank you for supporting our conference.
Thank you. I hope you like it. It was great.
Yeah, we are.
It was
We
good joining
are.
here.
Yeah. Thank you.